Hi, welcome to Math 331 problem solving. It's been a while. I'm Professor Miller. Good to see you all again. It's always tough when you come back from a break. So what I want to do for the next few days is just continue to go through Putnam problems. And our goal is to get you to the point where you can do 2 Putnam problems on the exam. If you do that, that will be a phenomenal score. Out of 120 points, if you get even 1 point out of 120, you're already doing better than most of the people who take it. And for the most part, only people who are strong in math take it. Okay? Just for the record, in case anybody is watching this who is not enrolled at Williams, I will just go back to the problem we were discussing last time with the zeros and the ones. So we were looking at numbers of this form that were prime. And we showed we could write it as 10 to the 2n plus 10 to the 2n minus 2 plus 10 to the 0. And that's 10 to the 2n plus 2 minus 1 over 10 squared minus 1 using the geometric series formula. And then we almost had it last time. We just used the fact that a squared minus b squared can be written as a nice factor as a plus b times a minus b. So this is just 10 to the n plus 1 minus 1, 10 to the n plus 1 plus 1, divided by 9 times 11. All we need is that each of these factors is greater than 1. If you divide by 9 or 11 or 99. So if each of these factors is greater than 99, then we know since everything has to be an integer, we will have written our number as a product of 2 numbers, both of which are greater than 1, and thus the number can't be prime. So once n is greater than or equal to 2, these numbers are too large to be 99. If n equals 1, notice it could be 99. And so if n equals 1 or 0, you have to check those cases separately. If n equals 0, the number is just 1, which is a unit. And if n equals 1, the number is 101, which is prime. So the only prime number of this form is 101. So we were extremely close last time. We had the right idea to use the geometric series. Again, for these problems, these are not life problems. These are math competition problems. There should be a nice, elegant way of looking at it. And if you see that, if you start to see this, you know you're on the right path. If you are not seeing it, this is similar to my proof of Morley's theorem. You may get there, but it may be ugly and time-consuming. Okay, one of the problems I wanted to do was the first problem. I have no idea if this will work. The first problem, which is the one with triangles and rectangles. Did anybody look at that one?
Do you have another copy of that?
I do.
You have 2 other copies of the package.
Yes. All right. Okay. Do you need a copy? I bought more copies. Anybody else need a copy of the problem? Anybody else? I might have given away too many. I think I actually gave away too many. All right. I remember it though. Does it say what year it was?
1985.
1985. Does it say if it's A1 or B1? Okay. So and it's an acute triangle. So you have an acute triangle, and what you want to do is you want to have a rectangle and then another rectangle in this, and you want to maximize the area of the rectangles. Okay. Did anybody solve this? So I have a couple of approaches that I want to talk about. The main idea is the thought process to me. I doubt there will ever be a situation in your life where you have some kind of triangle room and you're stacking boxes and you're trying to see what's the maximum volume or whatnot that you could stack in an attic like this. The first thing is to see what kind of symmetries can we look at. Or can we take an easier case and try to build intuition? So the first thing to note is if I drop a perpendicular down over here, I have problems on both sides. And to some extent, it would be wonderful if whatever I do on one side is mirrored on whatever I do on the other. Now, this angle is not necessarily the same as that angle. So you want to be very careful that your picture is not misleading. So in fact, on this side, maybe I'll come down sharply to make it very clear that this is not the same angle on both sides. But it would be interesting if I could show that I've got three lines here. This length, this length, this length. If the argument on the left side is the same as the argument on the right side, then it doesn't matter and I can consider everything independently. Because otherwise, if there was something better to do when you're considering rectangles, well, when you just draw the line here, you can't do better than each one. So I'm not going to try to make that sound better. I just hope that seems reasonable, that it might be enough to just initially do it when we have a right triangle. What right triangle might you want to study? So what kind of right triangle might you want to study?
45, 45.
Yeah, isosceles right triangle. Maybe this length is the same as that length. Just to build up some intuition, try to get a sense of what could you do and explore some cases. What might you do before you try to solve this whole problem here? And try to make it easier and easier and easier.
Do the case with one rectangle?
Yeah, do the case with one rectangle. So let's just build some intuition. And then we can see what really matters. So maybe I'll do the calculation with a 45, 45, 90 triangle, and then see if that actually helps me at all if I need to use it at all. It always helps to have good variables. The other thing is sometimes one problem is equivalent to another. Every maximization problem is equivalent to what? Yeah, there's a corresponding minimum. Imagine you only have a program that can find minima. It can't find maxima. Then just multiply your function by -1 and feed it into the minimizer. Not a big deal. Instead of trying to maximize this area, what could we try to minimize? Yeah, the area of these two triangles over there. So let's say we go up x units. Without loss of generality, what's the entire height? 1. So this would be y would be 1 minus x. If I go up x units, what's this length over here? So what's this length over here along with that? We know this is x over here on the other side. What would be this length? I'm sorry?
Also x.
It is not x.
Is it 1 minus x?
It's 1 minus x. This is the 45, 45 dimension. This is x over here. And so this is 1 minus x. And now you can begin to see why I'm looking at a 45, 45, 90 triangle. So if this is y, then this would be y over here. So I could want to minimize maybe 1/2 x squared plus 1/2 y squared, subject to x plus y equals 1. Or I could try to maximize x times 1 minus x, which is x minus x squared, subject to x squared, I guess, in this case. And again, in this equation, because it's so simple, x plus y equals 1, I can solve for y immediately in terms of x. So this is a parabola. We've seen stuff like this before. This should remind you of like the Farmer-Brown problem. We can use calculus. We can find out where it's best. And in this case, it's going to be best when x is equal to 1/2. So you can see this with calculus. If we wanted to minimize 1/2 x squared plus 1/2 y squared subject to x plus y equals 1, I could use multivariable calculus as well. And so what we could do is we could have f of xy is 1/2 x squared plus 1/2 y squared. G of xy is going to be x plus y minus 1. This is my constraint. And now I want grad f to be a multiple of grad g. Lagrange multiplies. And if I do that, well, this will just get me x comma y. So having the 1/2 in the triangle is actually nice. Is equal to lambda 1 comma 1. And I also have x plus y equals 1. So when I try to solve this, I see immediately that x and y have to be equal. So this implies x equals y, and then from that we get x equals y equals 1/2. So this is not too bad to do using Lagrange multipliers. And if we had more pieces of triangle, nicely. Now this is doing things with a right triangle. And in fact, not just a right triangle, an isosceles right triangle. How would things change if it wasn't 45 degrees? Do you think the answer would be different? So let's go through and so put a theta here. Now, in this case, which would you rather work with? Maximizing the box or minimizing the two little triangles?
The box.
I think in this case, with just one thing, I would rather maximize the box. But if I had more of them, if I had two boxes, I think I'd rather do the bunch of triangles. And so in this case, if this is theta, if this whole side is 1, you now have to decide how do you want to do lengths. Your theta is fixed. So if you have this whole thing is the hypotenuse, then h sine theta is 1. So this whole thing down here is going to just be h cosine theta. And so if I go up x units, then I've got to figure out what everything is. All right, so if I go up x units here, what's this distance? So you can use corresponding parts of congruent triangles are congruent. There's lots of different ways you can do it. X is to 1 as this is to h cosine theta. All right, so if we call this little part down here w over h cosine theta is the same as x over 1. So w is x h cosine theta. And so we get the box is going to be 1/2 this distance here, which is going to be h cosine theta minus xh cosine theta times x. Oh no, so there's no 1/2. Because it's a box, it's not a triangle. Well, notice we can pull out the h cosine theta. We get h cosine theta, and then we get 1 minus x times x. And notice that it's not going to depend on the angle. This part over here is fixed. H is fixed, theta is fixed. So the analysis we did before, it's the same function to optimize. So it looks quite likely that the answer should be independent of the angle. And again, you have 3 hours in each session. You have 6 problems. Take the time and really carefully explore a problem. Try a couple things, get some data, build some intuition. One of the biggest freezes people have when they take tests like this is that they feel that if they don't have anything right to put on the piece of paper, they shouldn't put anything down on the piece of paper. No. Fill the paper with ideas. Don't worry if it's a good idea. Try to do any calculation you can related to the problem and start building up some intuition. Start seeing what's going on. And what's nice about this is now we see that it's not really mattering, that there's just a scale factor. And if that's the case, then it would be wonderful if it's just a scale factor if we had more pieces. And then we could just consider the easy case of a right triangle that's isosceles and then generalize. So let's look at the next case. And I will write not to scale. So let's assume it's still 45 degrees for now. So if this is x, and this is y, and this is z, if this is x over here as well. It's a 45-45 triangle. If this is y, because that's also 45. And so this is z. So we want to minimize 1/2 x squared plus 1/2 y squared plus 1/2 z squared, subject to x plus y plus z equals 1. And this is ideally suited for Lagrange multipliers. So we would get the gradient of f is going to be, the 2's cancel, so we'll just get x, y, z, and that has to be lambda 1, 1, 1, which is the gradient of g. And again, I'm not explicitly writing it, but f is just 1/2 x squared plus y squared plus z squared, and g is just x plus y plus z minus 1. So, as before, we get x equals y equals z, and now they just equal 1/3. And that would solve the problem here. And what we've seen is that if we have a right triangle that's isosceles, that the best we could do on this side is to have a third, a third, a third. Then correspondingly, the best we could do on the other side would also be a third, a third, a third. And so when we put them together, there can't be something that's better, because if we then just drop the line from the top vertex, it would have to be winning on one of the two sides, and it can't. So all we would have to do now is show that if we change the angle, it would just rescale things. Well, that's going to just rescale these lengths by a cosine theta or 1 minus cosine theta and h, something like that. So it doesn't really have to be 45, 45, 90. All right. The way I was trying to look at this problem to try to get some intuition, so I don't like this solution. It is a perfectly fine solution to use on the Putnam. It is only using multivariable calculus. To some extent, I almost feel like you should be able to avoid multivariable calculus. That when you have an answer that's as nice as 1/2, 1/2, or a third, a third, a third, and you can see what the general case is, there should be a good argument lurking. And so I was trying to think, what could be the good argument? And so imagine we, convert the triangle to a square. And now we're basically removing certain pieces. And so we want to remove the smallest thing we can, like that. So we're choosing a couple pieces on the diagonal, and at each of these pieces, we're using these as extreme corners of squares to remove. So if we think of it like that, let's do the case n equals 1, where we just put in one piece. The problem they give us is n equals 2. So you have to choose a point over here, and then we'll form two squares like this. And you can slide this point, and as you slide the point, it changes the area of those two. Where should we put this to minimize the sum of those areas? In the center. Can you prove that without calculus? Again, you know calculus. You may use calculus on the Putnam. I do not want you to avoid calculus. But sometimes if you step back and try to think fundamentally what is going on, it's a worthwhile experience. So I can mimic calculus arguments and avoid actually using calculus. Let's imagine we have a point over here. If I move this point up a little bit, let's think what happens. I lose this region here, and I gain this region here. So really, I'm losing those two things up here for those two things down here. If I'm below the midpoint, I'm losing more than I'm gaining. And that's a good deal. Is this a calculus argument? I'm not taking derivatives. I am looking at how areas change. But I'm not formally taking a derivative. Yes.
So would having some kind of graphic example like that be good enough for the Putnam?
If you can write it up really clearly. I have a friend who left mathematics. I mean, he was never going to be a mathematician, but he was taking the advanced freshman math class at Yale, and he proved that something was an integer. He proved it was greater than 0. He proved it was less than 1. He therefore concluded contradiction. He had it was equal to a half. The greater than mode, you never showed that 1/2 is not an integer. He found a home in chemical engineering. So the question is, come on. If you know who's doing things, you're often a little bit more free with the proof. By now, hopefully you understand I actually do know some mathematics, and that I could make this extremely rigorous. I could write down exactly how much things are changing by as I move this, and I'm sliding it. Given that you will almost surely have time, spend the time to write it up carefully. But to an extent, I would say, when you're sliding this, if you're less than half, you need to just show that these two really are greater than those two. And the idea is, if you're more than halfway down, this line is bigger than that line. And they all have the same thickness.
And for it being greater, like past the midpoint, you just use symmetry.
Exactly. So by symmetry, you only have to go, and this is of course one of the advantages of looking at a 45-45 triangle, is we do have that symmetry. And again, it's sometimes not a bad idea to take some time and just build intuition. And then say, look, without loss of generality, we can assume that it's a 45-45-90 triangle, because if not, all it's doing is it's rescaling things by a fixed factor. Another way of looking at it is I'm measuring vertically in feet, and I'm measuring horizontally in meters. And they don't have the same scale. Right? If you are building a probe for NASA, and this actually happened, this is bad. All your measurements should be in the same system. There's now a $25 million crater in Mars, because as the probe was descending, all the subsystems were in metric except for one, which was in the English, and it miscalculated how much thrust it needed to land safely. And so there's now a $25 million crater on Mars. Okay? You have to be careful. But here we can do essentially a change of variables and just squish the triangle, and it's not going to really change anything. So are people happy with this in one dimension? I'm sorry, with just one cut point. Now, we have multiple cut points. Can you apply that argument here?
Can you just scale it down to 2?
So what we could do is fix this cut point here, and then if this cut point is not at the middle, it's not optimal. And then if this is not at the middle, it's not optimal. So what you could say is, if there's a situation where each of these is not a third, a third, a third, we could always slide and do better. There's a subtle mistake, and I know somebody was asking me before class about real analysis next year or next semester. We don't know that there is an optimal solution. This is where you have a great result from real analysis. A continuous function on a closed bounded set attains its maximum and minimum values. So that there is a way to slide these things and get to a maximum or minimum. You need to use that result somehow. Technically, what should I have done when we did the Lagrange, when we did the calculus and the critical point? I should also have checked. I should have checked the endpoints. But it's pretty clear that you're going to have terrible area if you're drawing the dot over here, or the dot all the way up there. So I didn't bother checking that. You technically should, and you should write down it's 0 in those cases. So the difficulty, and we saw this before with some problems, review the review the arithmetic mean, geometric mean inequality. That's an extremely important one. You sometimes do not know a priori that there is a optimal choice. But you can quote this result from real analysis. A continuous function on a closed bounded set attains its max and min. So that there will be a choice of points which will lead to a maximum value, and there'll be a choice that will lead to a minimum value. It's extremely important that you have a closed bounded interval. If I give you the function f of x is 1 over x, 1 minus x, 0 less than x less than 1, the function is blowing up as we approach. And you can do other games if you want, so that you can get it so that it has no minimum and no maximum. This at least has a minimum. Okay. Does anybody have any other words they want to add about this problem? So I liked it that you can solve it using Lagrange multipliers. You can solve it using calculus. I think you can make this argument rigorous as long as you appeal to this fact from real analysis. That there's going to be a choice. And if you have a situation where they're not all equal, well, then just slide one of them. Because if you have a situation where they're not all equal, this one, say, doesn't equal that one, or this one doesn't equal that one. And then you either look at this big square down here, or you look at this big square up here. And then you just slide it. And that contradicts the fact that you're at a maximum. So there's a little bit of a proof by contradiction lurking in the argument here. Okay. Any other questions on this one? Yes.
So really quickly, isn't that argument to say that like the 1/3 solution is greater than like anything else, right?
I would say it's less than anything else.
Sorry,
it depends. We're now talking about these triangles versus the boxes, but yes.
So I'm a little bit confused on why you need a continuous function attains its max and min. Like even without that, like doesn't the argument?
How do you know a limit exists? How do you know there is an optimal point?
Because of your argument that if you're anywhere else that you can do better up until.
Right, but maybe there is no best. This is the annoying technicality. What I'm saying is, if you're in a situation that's not a third,
Right.
you're not at the optimal, so you can flow.
Right.
But maybe the flow never changes. Maybe it never stops. Maybe you're constantly flowing. Maybe you first adjust this point, then you adjust this point, and you have infinitely many adjustments. That's the annoyance. And that's what this theorem allows you to avoid, is that you don't have to do this infinitely often. That there is an optimal. Now that we know there's an optimal, let's assume the optimal doesn't have a third. So the other points to really emphasize about this is essentially the only time in your life where you can spend this much time in a class on one problem. They can hide what you should really look at. You can attack the problem directly like this. I think it's much easier to look at the situation where you have just one point first, try to understand that, and then extend that. Because really, if they're giving you two rectangles, you should be thinking, this is the general case of n rectangles. And try simple cases and try to detect a pattern. The other thing is, if you're ever asked to maximize something or minimize something, there could be a complementary quantity that's easier to work with. And I didn't like how this is x and this would be like 1 minus x if I'm doing the initial one. I actually like the fact that this is x squared, y squared, z squared. All right. Any other questions on or comments on this one? All right. I think we have beat this problem to death. For the record, it's only around 10:31. So we've spent less than a half an hour on this. With all of our discussions and all of this, that took less than half an hour. Now, admittedly, this is starting with a professor who had thought about this problem over Thanksgiving and had some idea of how to discuss it. But just to give you an idea, 3 hours is a long time. So don't be afraid to spend a lot of time. It is much better to spend the time and get 1 or 2 problems correct than to be close on a lot of things. You should, of course, look at all the problems because they might have the problems in a different order. Typically, they are supposed to get harder as you go deeper down, but sometimes one problem will just resonate. All right. Does anybody have another problem they want to discuss?
Do we ever talk about 2017 A1?
I have absolutely no idea. I don't think so. Which one is that?
It's like the
No,
first button
we
problem.
didn't.
Okay. Can I borrow someone's here? Can you two share? Okay, so 2017 A1. Okay. So either somebody is moving or lightning and thunder is approaching or a horde of wildebeests. Okay. So S is the smallest set with the of positive integers such that the following things are true. 2 is in S. I'm going to write if n squared is in S, that implies n is in S. And C, if n is in S, then n plus 5 squared is in S. What is S complement? So this is the things that are not in S. Okay? So can anybody give me a number that is not in S? Yes.
1.
Okay. I was. Okay, good. It says which positive integer. So I was thinking of 0, but yes. So we know 1 is not in S. And to see this, we know that 2 is initially in S, so S is not empty. If n is in S, n plus 5 squared is in S. Okay, that just makes things larger. And then we can take square roots of perfect squares. Okay, so clearly I agree that 1 is not in S. So what we can do is we can have S complement. So we have 2 data points. So I would say 50% of all integers are in S and 50% of integers are in S complement. Okay, probably a bad conjecture. Do we have any other numbers that we know are in S? Yes?
49.
49?
Yeah, that's true.
That's the next one.
Well, 7's the next one.
Well, but
It
so,
depends on which.
so this is an interesting question. Which is the next number you find out?
49.
Technically it is 49. So, great, all the way to Tommy we have 49. Now that we know 49, now we get 7 as the square root. So 2, so we have 3, 4, 5, 6, we don't know, we have 7.
I mean, everything of n plus, like, 2 plus 5n is in S.
2 by 5, yeah. Because now it's going to have.
Right, so from C, we immediately get n plus 5, n plus 5 squared is in n, we also get n plus 5 is in n. Right, so we know we have 7, we have 12, 17. Okay. So we know n is in S if n mod 5 equals 2. So we've now handled 40% of all integers. Not bad.
20%.
Oh, I'm sorry?
20%.
Oh, 20%, sorry. Not as good. Yes.
We can also say n is in S if n mod 5 is 4 and n is greater than 49.
Right. So why do we get that?
Because 49 means we're going to have 49 plus 5, 54.
Mm-hmm.
So we're going to have 54 plus 5, and so on.
Right. This is why I was saying 40%. So n is in S if n mod 5 equals 4. So basically, once you get one number, did I make a mistake?
You say and it's greater than or equal to 4.
Oh, yeah. And at least 50. Zero is just easier to write. You know, I can just go into circular motion was 4. Of course, I now lost the time I saved by running the circle by justifying why I went like that. So the idea we're getting from this is once you get one number in a congruence, you can get everything from that point onward. The problem is the square roots could allow you to come back and get some of these numbers. Okay. Any other thoughts? Yes.
So 54 squared will get you
How do we get 54 squared?
n plus 5 squared minus 49.
Oh, okay. So you're saying, okay, look at 54 squared. Okay, yes.
Right. So then that'll get you something with a 6 in the ones digit, right? And then if you do n plus 5 on that, basically you get n mod 5 equals 1.
Okay. So n is in S if n mod 5 is equal to 1, and at least,
Like 2500.
so,
If that's easier to write.
well, so we wanted to do 54 squared?
Yeah.
Okay, so 54 times 54 is 2916. Yes.
By the plus 5, we're at 49, 54, 59, 64, and then
Okay.
we get 8.
Okay, so we're good. So from the 64, we get 8. And 8 is going to give us 3 mod. So n is in S if n mod 5 equals 3 and at least 8. So the only thing that's left are the multiples of 0. So do we think that we'll ever get anything that's 0 mod 5? So if you were not 0 mod 5, when you take the square root, you're not 0 mod 5. If you are not 0 mod 5 and I add 5, you are still not 0 mod 5. All right. You know, S complement is at least not going to be destroyed. Right? All 0 mod 5. All right, so it's not 50-50, but it's at least making a decent showing. All right, so now we are down to, is it a finite calculation, yes or no?
Like of how many integers are not.
Right, so for instance, do we have enough here to say that it's a finite calculation and all you have to do is take a piece of paper and check finitely many things and you'll be done?
Yeah.
How would you do that check? Because the issue is, for instance, you got 64, which when you then took a square root gave you 8. So while it might be a finite calculation, it may take us a long, unless we can actually get a number. That's the problem. Is how do we know we can't get a 6? So you could start trying to play the games, well, if we're going to get a 6, we had to have a 36 somewhere. Or we had to have a 1. We're clearly not going to get a 1. So could we have a 36?
Well, if you have a 36 squared,
Right.
I'm sorry?
If you have a 36 squared, then
We need a 31.
Then you would need a 31. And you have to keep playing this game. Right? So the question is, if the numbers are representable, you should be able to take it and iterate and find. The problem is if they're not, then this chain of arguments could just keep on continuing. So do we have a good way to determine whether or not, for instance, a number like 3, 4, 5, or 6 can be represented? Now the interesting question is, before we go further, how much credit do you think this is worth?
None.
I mean, to me, none is, even Kayla is not, well, Kayla might be that harsh. I mean, I would say this is definitely worth something.
1 point.
1 point. See, it says which positive integers are not an S. We've already established 20% of all positive integers are not an S. And we actually know from 2916 onward what's going on. Right? So if you want the number of integers we don't know is at most unsure of how much do we have. So we have 29 roughly, 16. We've got maybe 12 that are known here, multiplied by 0.8. So that's roughly maybe 2,300 numbers over the cardinality of the integers, which is all if not. So really, I mean, we're talking about 0% of the numbers we're unsure of. So if I was grading the Putnam, I would say that this is worth at most maybe 2 or 3 points. The real meat is probably going to be determining that. They might be a little bit more generous and say that, well, because we've now established everything from 2916 onward, maybe this is worth 6 or 7 points. I do not know how much they would give for something like this. And you do the best you can. So one thing you could do is you could try for some of these individual numbers, you're filling in the table and seeing when do we hit squares. So it was really nice when you noticed that we've got 64. So the question is, are there any other squares we would hit? And you can just try to go through the list and see when do you hit squares. Well, how do you hit squares? You've got to be walking up by 5s. So what you could do is you could start writing down the list of squares and subtracting 5s from them and see when are you getting something. So, again, I don't know if anybody has a solution to this, or just this look like a fun problem to discuss. I might start by just making a table and saying, look, I've got time to spare. Here is 9, 16, 25, 36, 49, 64, 81, 100. Oh, 100's not going to. We know we're not going to get anything with a 5.
You're not going to get 25.
We're not going to get 25. So 121, 144. So we're not going to get any of these numbers. Well, let's start walking, because if we know if n mod 5 is 4, then we win. So we want to start walking before this. So 9, what comes before 9 is 4. So if we get 4, we get 9. And in fact, if we get 9, we get 4 as well. So these two are now linked. I guess I should maybe go this way. The 16, that's 11. And then when we subtract 5, that's 6. So we're starting to get chains. You know, we know we don't get 1, so it's not worth going further. For 36, that's 31. Sadly, we only know things about mod 5 once we're at 2916. But so we can have these chains going down.
That'll get you back to 11.
And then after 21 becomes 16. So that's kind of nice that there's a chain like this. 49, we actually do know we get 49. Okay, so we don't have to worry about that. 64, we know we get 64. So, you know, 81, as we start walking back, we would have 76. Well, what are we eventually going to hit as we walk back from 81? We'll eventually hit 36. Yes?
So, I don't know if this is an intuition that's going to yield anything or not. But just like looking at that, like I noticed that it's like there are a few of those that are 1 mod 5, right?
Right.
Like I wonder, like what would happen if you like squared those maybe and then like got above 2, 9, 16.
Ah, so good. So start off with maybe 81 squared.
Yeah.
So if we took 81 squared, now but 81 is 1 mod 5, so when we square it, it's still 1 mod 5, and when we add, it's going to be 1 mod 5. So we will get 81 squared. So we will get 6561.
Is that bigger than the? Yeah. So does that mean?
So that eliminates.
If not, you could just square it again, right?
Yeah.
Right. So now the question is, do we want to start off with wait a minute. So, but we don't know. Wait a minute. But we don't know that we have 81.
No, the
No,
point
but
is
it-
that-
Wait. The point is to look at what 81 squared is, which would be 6561. Good. So we've got 6561. We can then take its square root. So now we know we get 81, and we get all this stuff coming down. And now I think we now are at the point where we're going to just really hammer
Can
this
you go
home.
backwards?
I don't think that.
Oh, can you not go backwards?
Because if n is in, then you get
Yeah, you
five
can-
squared, but you.
Yeah,
Oh,
if
wait.
n squared is in it, then you get n.
I don't think.
Oh, no, but we can't. No, sorry. No, that will get us 81, but it will not get us 76.
Yeah.
We can't subtract 5. We can only add 5.
How do you get 81? How do you get 81?
Because 81 squared is n, so n squared.
81 squared is it? Because it's equal to 1 mod 5. And it's
And it's actually
right. So what we want to do is we want to look at, say, for instance, 16 squared
Can we look at?
or 36 squared.
Yeah.
Can we look at like all even powers of 6? Because if
So
one
I
of them is in, then it
so
triples.
So if you take like a high enough power of 6, I think that will work. So we've got to go to the next class, but we can't subtract 5. But I think we're essentially there now. That once we get one of the small ones here, then we've got all the other stuff coming down from it.
Yeah. Just to be clear, when we get 81 squared, we get 3, right, from that? Because if we just square rooted and square rooted and square rooted.
Yes.
Oh.
So we would also get 3 from that.
Yeah, that's what I'm
Oh.
saying.
Yes.
Okay.
Yeah.
Yes. And so now once you have 3, that's really nice. Now you get all the numbers that are 3 mod 5 starting from 3.
Mm.
So that's a really good observation. So remember to email me. All right. This is a good place to stop.